My name is Obwakunye Buchi Augustine, and I am an electronic design engineer with expertise in PCB designs. Below is my work mail and my LinkedIn link. Okay. That's my contact there. So we'll be going through the agenda line now. So the first thing will be to recap on product design, but now with respect to PCB designs. And the next would be to highlight, put the flashlights on our case study, which is going to be a standalone 3S optimized battery charger. And then the next, we are going to talk about product requirements, specifications, constraints, and functionality with respect to product design using pointing at our products, our case study actually, sorry. So the next is going to be the actual practical section. There we'll be familiarizing ourselves with the Fusion Electronics Design Interface and doing the actual modeling. Okay, so moving on to the next slide. I would love to explain, or will I say describe product design as the process of refining products for users. Okay, there are many problems, there are many needs out there, there are many problems that needs to be solved out there in the market. So for us to create a product that will solve these problems, we need to actually go through the processes of product design. And with respect to PCB, it's actually the process of creating and refining printed circuit boards, which are just still PCB that solves user problem and addresses specific needs in a given market. No matter what the market is, so far you can just solve it, by creating a product, then that's the market we're talking about. And I would also like to throw more light on the principles of product design, which includes the understanding of the end user needs, creating a product that meets those needs, and also delivering a positive user experience to gain loyal customers. That is very important. Now, moving to the next slide. Well, case study is going to be a standalone 3S lithium-ion battery charger. And this charger is meant to be used on lithium because it's meant to be used on lithium-ion batteries. Yeah. And then one thing I would also love to say is that the reason for this product is because there actually are not much of these specific chargers out there. What you normally see there are just mainly for lead acid. So you see that creates that need for these kind of batteries out there, and most of those chargers are imported. So that's the need case that we'll be looking at here. So the next will be our product requirements, and we are going to go through it a bit. But before I continue, I also love us to get our questions ready and then ask me with time. So product requirements are actually the features and characteristics that our PCB, which we are designing, must have to meet the needs of the customer. These requirements can include the size of the board in respect to the product size, number of layers, and types of components. And I don't know, I believe that you must have been taught about printed circuit boards and also the layers at which they come, But also I also love to, throw more light, a little bit light on that. Okay, so the thing there is that products, the layers of a PCB, is determined mostly by its complexity. Okay, if you are designing a simple PCB, you are okay to make it 2 layers. But if you want to, if that PCB is meant to be very complex, and also you also want to add on something like designs, maybe company logo or something, that's where you have to add more layers or customize layers, yeah, for it. So for the second requirement, we have meeting standards for PCB design aspects such as schematics and thermal management and also quality assurance. Now, in explanation to this, thermal management here refers to the design and implementation of strategies to control and dissipate heat generated through the operation of electronic components. All right. Then for our schematic, throwing more light on that, um, is simply, sorry, okay. For our schematic, is simply, our product is required to, let us say, okay, for example, with respect to our case study, charge a battery. You can't just go and get another, or you can't draw or model a schematic. You can't draw a schematic that will be meant for toggling of light alone, just because you think it's an electronic product and you're designing a PCB. So you just have to give the product, the PCB, the required schematic for it. Now, I've explained the thermal management and showing more light on the quality assurance. Sorry. Okay. Showing more light on the quality assurance. This actually plays, mainly on the side of manufacturers. All right. As an engineer, as a design engineer, you have to work in hand with the mechanical engineers and also the manufacturers. Now, you guys will have to go back and forth till you find a very balanced plane where you guys can establish everything that will suit the product perfectly. Now, using quality assurance, for example, on the part of the manufacturers, here I think quality assurance actually refers to the systemic processes and practices to ensure that the manufactured PCBs meet specified quality standards. Now, I will throw more light on this. Okay, I will explain this more. So, like I said, I repeat again, this refers to the systematic processes, all right, and practices that ensure that the manufactured PCBs meet specified quality standards and performance criteria. This includes maybe various activities that goes on throughout the development of the PCB to minimize defects, enhance reliability, and then meet customer expectations. And these things involves design validation, going through the design and making sure, okay, that what, like I said, um, when once you design, you have to communicate with the manufacturers to know if they are okay, their manufacturing dimensions, for example, are okay with your set dimension. We'll be going through that during the practical sections. And also talking about the reliability, this is about reducing defects, with respect to mistakes and let's just say you have maybe you made a mistake or you let's just call it a mistake, or you were wrong in somewhere, you designed you set a parameter that didn't meet up with the manufacturer's parameters. So these are the kind of stuff where you have to discuss with the manufacturer going back and forth. So to minimize defects and also to enhance reliability, you know, that so that your product can be able to work for 1, 2, 3 hours, 2, 3, 4 days, 1, 2, 3 months without any issue. Yeah, so and also to meet customers' expectation because in this part there is no way your product will be useful if it doesn't meet the expectation of the customer. So let me just recap this whole thing again so that it will be smooth now. So product quality assurance actually means the processes and things done to ensure that the manufactured PCBs meet specified quality standards and performance criteria. So moving to the next, we have our right board size. And this size, that's the third point. This size, let's just say that you want to design a big sized product. You want this charger to be big. Normally, this one that we designed, our case study is not big, it's small. Well, I say it's medium. So if you want it to be big, so what are you going to do? You have to communicate with your mechanical design engineers, and then you aligning with them will bring out the perfect board size. Once they give you their own measurements, you can then work with it to actually know how you are going to model your 3D, your schematics, and your PCB, both your 2D and 3D. So next will be the trace width, which is nothing but the copper linings on that you normally see on PCBs. Um, excuse me, please.
Are you still talking? I know you're muted, like your mic is muted.
Okay, sorry.
Is there any challenge?
Yeah, there was an interference of
Okay, go ahead.
construction noise in the background, so but it's not okay, aggregated.
Okay, go ahead.
So as I was saying, that okay, so starting from the quality assurance, um, like I said, it's mainly for manufacturing, but as a PCB design engineer, you also have to know about this. You also know about it. So it's more like it's much of the system, it's all about the systemic processes and the practices, you know, done by the manufacturers to ensure that the manufactured PCB meets specific quality designs and standards. and performance criteria too. And you also, as a PCB designer and electronic design engineer, also have to take that in, you know, also have to have that in mind. So, like I said, it includes the various activities throughout the PCB development, just to minimize the defects and also enhance reliability and meet customer expectations. Now, this involves design validation, material selection, and respect to um, material selection and choice of components with respect to industry standards and your local markets. So manufacturing for the manufacturing process control, testing and inspection. So these all falls under the um, requirements for standard PCB designs. And let's talk. I'm talking about the thermal management. Now, concerning the thermal management, this is actually the manufacturing process and also the design processes that ensure that, hello, to ensure that the products that the PCB that we are talking about here, designing, actually works out well and handles thermal energy, heat handles it well. So um, the third one would be having the right both side. Like I said, you have to work in hand with your mechanical design engineers in their department and also with the manufacturers. Now, working in hand with the mechanical design engineers with respect to the board size is it all boils down to the product size. If you want the product size to be big, or if the product size is supposed to be big or small, now it depends on the dimensions that um you will be working with, the dimension of the work of the PCB that you'll be creating. Let's just say that the product was meant to be very small. Now, in that case, you have no other choice than to resort to um in that case you have no other choice than to resort to SMDs using tiny components. But during the prototype section, during the product design stages, as you were taught, you can be working with the normal you can be working with normal through hole components, the ones that you find locally. But then when it comes to manufacturing, due to the size of the PCB, you can then send, you know, you know, replace in, put in place where the through hole components are the big components, put in their place the SMDs, the onboard components. SMDs are those components that are being soldered on the board. If you get a PCB, you will see some components. You notice that some components pass through the hole all over to the other side and they are soldered on the other side. But you also get to see example is ICs and some capacitors and resistors. You get to notice that they are actually placed and soldered on the board. Not it doesn't pass through, no legs, just um lead headed ends to push the solder the board to we push the solder we push the solder to the board. So the next stuff that we will be talking about under this third point is actually the trace width. Now the trace width is actually those lines that you see in a PCB. I will just use my next slide for an example. Okay, we're not yet done with the other slide, but I want to use this picture here as an example. You will notice the lines through the PCB. You notice the lines through the PCB, and also you will notice the lines, the connection lines going all around the surface board. That's the back. And um what these lines going all around the surface represents are actually the connections, the onboard connections. That is what I am talking about when I say trace width. Now these lines, these traces that you see, the width is actually what we are talking about. You can increase the width or you can reduce the width. It depends. And it's also have its own limit of, increment, and also limit for decrement. So for the holes you see, that's where the through hole components pass, something like the normal big resistors that we see that has two legs. Yeah, stuff like that. So getting back to the recent slide to complete. Okay, now we'll be talking about materials. Now for materials, that's still where the components fell into, because let us say that our company is meant to be big. All right, our company is meant to be big. The choice of material, the choice of components that we'll be choosing, and also with respect to the manufacturer, the choice of materials that they will be working with, and providing our required PCB also varies with respect to the number of layers, and also what our PCB does. If it's one that is required to withstand a very big amount of heat, then the materials are also there for it. They will see to that one. Now for there's also component placement. That is where you arrange your components, know how to take up advantage in spaces, and because you are trying to achieve a small sized product, right? And also tolerances. You have to create tolerances. If let's just say, for example, something using something like okay, our environment, our charger here, for example, um it's meant to charge. Okay, let's just say we want this charger to charge to charge a battery using 5 amps, all right, or using 3 amps, for example. Now if you want to do that, you have to get and you are looking for a diode for that, you have to get an actual higher diode, and then look for a way to, using voltage regulators for current steady for steadying the current, sorry. So using voltage regulators to provide a steady current, then using such what do they call it, the diode. I mean, that's an example of tolerance. Then another example of tolerance is okay, let's just say that we have an inverter, and this inverter, I want to design an inverter that charges that delivers 1,001 kilowatts power. Okay, 1 kilowatt hour. It charges a battery, or it charges anything, or you can run anything on it. The power is 1 kilowatt. You are actually going to make it 1.5. That 1.5 is actually tolerance, and I believe that you must have been taught these both in the mechanical aspect. Now that tolerance is there as the reason why that tolerance is there is because some users might want to overload or overuse the product, the device. And what this is going to cause is that what is going to happen here is that if these products doesn't have any tolerance, once they exceed that 1,000, for example, using the inverter, for example, once they exceed that 1 kilowatt hour, that's 1 kilowatt, once they exceed, the device blows up, or maybe the device goes, like the device dies down. All right. But if it has been extended to 1.5 kilowatt hour, then 1.5 kilowatts, then nothing will happen to the device. All right. But you can still put an indicator, as a warning that says, hello, user you are overusing these products. And in that case, if anything happens, you are sure that you gave a warning, and that also makes your product to stand out. And that's it. Then another one, the last point, which is simple and cost effective locking mechanism. For this simple and effective locking mechanism, you get what you do here is that what is required here is instead of using complex schematics, you will look for something simpler. All right. Let's just say that you want to design you want to make a bulb to just light on and go off. All right. And you want to make it you know to design it using to go on, light on, then go off, in a space of 2 minutes or in a space of 1 second or 3 seconds. Now, instead of involving big schematics and introducing big ICs, making it an overkill, okay, using something like an Arduino to just get that done. That's much of an overkill for just such a simple circuit. You can actually use the 555 timer or design a capacitor circuits to actually get that done in no time. And that's it. And also you realize that this doesn't only make these products, it doesn't only make your design simple, it also makes it cost effective. So for the next slide, we'll be moving to our product specifications. Now, talking about product specifications, I'll continue, but I would like to know if there is any questions, please.
I have a question.
All right, go on.
You mentioned voltage regulator.
Yeah.
My name is you mentioned voltage regulator in this I think tolerance. So is the work of a voltage regulator similar to a resistor, like limiting current or limiting voltage system?
Okay, no, it's what a resistor does is to limit voltage mainly, all right? And for using a voltage regulator, and you can use a voltage regulator to reduce or to limit current, and also you can also use it to limit voltage. Taking for example, the LM317 is a voltage regulator that you can use to, it's mainly used for limiting voltage, but there is another configuration that um puts it into that phase where it limits current, and you can actually manipulate your weight around that through calculations for it. There's a formula meant for that, and it's specified in the data sheet. But for if you want to limit current using what they call it, the resistors you said, did I answer your question?
I didn't get the last part.
Okay. I said that you can use both. Both. One is more like an overkill. All right. And if you are talking about current or voltage, you can apply that using the voltage regulator. And then I gave a specific example. All right. I gave a specific example of one voltage regulator, which is the LM317, LM317. And the voltage regulator, I said on it that it has this phase where this configuration with which you can use it for the regulation of current, and also you can also use it for the regulation of voltage. So with the resistor, let's just say that you want to reduce with the resistor everything is limited, but with voltage regulators you can actually limit high amount of voltage and current. but with the resistors, they are just limited. I don't know if I answered your question.
Okay, so you can say that a voltage regulator, the work is similar to voltage divider. Is it what we are saying here? I'm not getting you.
Okay. So a voltage divider consists of resistors in series. And these resistors, it's like I said, resistors, not one, not two. And it depends on the voltage that you're talking about. And there are some certain well, it depends on the voltage that we are talking about. And let's just say, for example, if you are talking about big DC voltages, that you still have to need a voltage regulator, because unless you want to use enormous amounts of resistors, which are still going to burn out faster than voltage regulators. And voltage regulators has their own advantages. As a result, I mean, they have their own breakdown voltages, and these things are being spelled out in the data sheets. Are you with me? So you can say that their work is similar, but if you want a more sophisticated approach, then you have to go for um the voltage regulator. But if you are looking for, if you are heading towards you are working on a very small circuit, let's just say you are designing something with Arduino, let's just say a mobile robot, with 4 tires or 2 tires, or you can still use your normal resistor, your voltage dividers.
I still have one more question. If we are talking about 5 timer, can you hear me?
Yeah, I'm with you.
Yes, the 5 timer. Can you repeat what you were saying concerning it, please?
Okay. So you can trigger. Okay, let's just say I mentioned what I mentioned with respect to the what I was saying when I mentioned the 555 timer was actually nothing but the triggering of an LED bulb. All right. And I was using that as an example, being our goal. Okay. So as I was saying, that was with respect to simplicity, which is the last point. So using simplicity and cost-effective mechanism, you can't, if you're working on a circuit that's okay, you want the circuit to just simply trigger an LED for 1 minute, to trigger an LED for 1 minute and then take it off, to trigger an LED for 1 minute and then shut it off. Instead of going for something more sophisticated, for example, using an Arduino code for just triggering an LED and then on and off, you can simply, maybe you can just, it's better that you use a 555 timer for that, because 555 timer is more simple and direct. You don't need any programming for that. But with the Arduino, you will definitely need to write some C programs, C++, the Arduino coding programs to the microcontroller. So moving over to the next, which is product specifications. Product specifications are the detailed descriptions of the product requirements. They are more like finely defined requirements, fine definitions of the product requirements. They define the exact parameters that the PCB must meet to satisfy the customer's needs. All right, and these specifications can include the electrical characteristics of the board, the mechanical dimensions, and the environmental conditions. Now, explaining these one after the other, the electrical characteristics refers to the properties and parameters, that relates to the electrical performance of the board. Now, this includes the impedance of the board. We all know what impedance is now, the resistance of a component, or okay, in this aspect now, the resistance of this our PCB board to AC flow. All right. So the signal integrity, which is the measurement of the quality of electrical signals that they propagate, that is being propagated through the PCB, and these will include signal distortion and timing issues. Then the next one is crosstalk, and crosstalk is it happens when a signal or a signal on one trace. Remember, I explained to us what trace widths are, the traces that you see on this surface mount, on the surface of the PCB surface, the image there. So the can you hear me now? Okay, okay. So the crosstalk it occurs when the signal on one trace interface with another signal on the other trace, or a nearby trace, or another, even another section. And excuse me, sorry. So it's when a signal on one trace interfaces with signal on the other traces. Another thing is voltage levels, current carrying capacity of the board, then the ability of the PCB material to actually withstand high voltages, without breaking down. Then another thing is the EMC compatibility. Now I'm talking about this EMC compatibility. It's all about the PCB not emitting unwanted electromagnetic interference, and it is not susceptible to interference also from external sources. Let's just say that, for example, I don't know if you have been in a church where the amplifier, maybe the pastor is talking, and then before you know it, another church another church program will be heard in your own speaker. That's frequency, that's interference, but on a frequency level. So these things can be covered through shielding, actually, that is conductive coating, or, metal shielding, a metal that acts as an antenna, enclosing the sensitive components of the PCB, where you have antennas, or sections of the PCB where you have sensitive components that can cause that. Now, another thing, how to shield, also how to how to protect or achieve this EMC compatibility, also involves the proper grounding of the PCB, to ensure low impedance, and that is it for this side. So for the mechanical dimensions, the specifications all lies in the dimensions, all right? And you have to, this is where you have to work hand in hand with your mechanical design. That is where you work hand in hand with your mechanical design, and get to achieve a product that corresponds to the actual size. And I'm hearing a noise. Are you still hearing me? Okay. So yeah, mechanical dimensions, so that you work with your mechanical team, the engineers, the team of engineers, and be able to get to realization a product that actually suits everything, that actually suits what is being needed by the users. Now, the environmental conditions also, points towards these mechanical dimensions, you working with them and stuff like that, because it also relates to the manufacturers also, because they have to put these things through some tests, and then some tests like thermal, is the product being used in in a riverine area or maybe in the sea, let's just say boats, you know that there will be high exposure to water and also the temperature is going to be cold. So it's always going to be cold. So you have to just identify if the component that you're going to use, the circuits, everything, if it can be okay, if it's going to be okay with water touching it. And normally, you know, the electric circuits, they don't like water. So you have that will also give rise to your mechanical engineering team, you know, building a more enclosed cover for the product and all that. So moving to the next slide. This is where we talk about the product constraints, right? And the product constraints, are actually nothing but limitations. You know, constraints. When we talk about constraint, we talk about limitations, the extent to which we go in some things that we do. So our product constraints are actually limitations that must be taken into account, you know, when designing our PCB. All right. And um, these can include the available space, the budget power, the power budget, the signal integrity requirements, and the manufacturing constraints. So when we talk about available space actually refers to the physical area on the PCB where components, you know, traces and other elements can be placed. So you remember I mentioned something with respect to size. So you also have to take that in, you know, you have to have that in mind. And it also involves the dimensions and layouts, considerations of the boards. So that's just it. So you as a designer, you must optimize the placement of components within the given space of your PCB to meet the product form factor and functionality requirements, you know. So coming to the power budget, here the power budgets actually involves the allocation and you know the distribution of electrical power within the PCB. So it's all about the let's say maximum power consumption allowed for each component or section. So let's just say that you want to create that, okay, this product is meant to take in, you want it to be conserving, all right? So you don't want it to consume any power. Let's just say, okay, we are designing a small robot. Okay, let's use our charger, for example. Okay, so let's say, okay, we want this charger to consume, this battery is supposed to recharge at 12 volts, 12.6 volts, with 5 amp of current or 3 amp or 1 amp, depending on the quantity of charger that you are, depending on the quantity of battery that you have for a particular product, you want to inculcate this, integrate this product, this charger into, let's just say, fan. All right. I don't want the thing to be heavy, so you just have to, you know, make the battery not too much. So in that case, you will have to be choosing your components wisely to know which one that we consume power the most and which one that we consume power less. And then in that way, if it's suitable and gives you the same result, you can substitute the one that consumes power lesser for the one that consumes power the more. So the next thing is actually signal integrity requirements. And here it talks about the reliability of electrical signals, you know. Um let's just say the signals, remember we talked about signals, the traces that you see on the bottom part and also the top part, the surface of the PCB, those are signals passing. And the reliability of these signals are actually what is being discussed, what we are going to be discussing in these section, this point. So the thing there is that you just have to maintain a good signal integrity because the thing is it's very important and also it's needed for essential for proper functionality, and these just include signal. This talks about signal distortion, noise, and timing issues. Remember I told you about signal protection where you have to shield. You have to shield the signal to avoid EMI that are not wanted. So this is where we thought when you are able to actually protect your signal and get your, let's just say we are working on a frequency based or frequency rely product, you won't want a situation whereby the product will start interfering or in the process of it being used, you start hearing when just the way you normally hear in the normal amplifier that we use. And that's also happened due to wrong settings and stuff like that. So that's the thing there. The next one is manufacturing constraints. Now, these manufacturing constraints actually involve the limitations, the limitations that are imposed by the PCB fabrication and assembly processes. Let's just say that the manufacturing company cannot, let's just say that manufacturing company cannot provide some components that which okay I haven't experienced this one before, but let's just say that you are designing something and the manufacturing company cannot, they don't have access to such components. So what you have to do is to look for a way to suit into their own set of components that you can use for your design, and this happens if you must or they are the only ones to manufacture your product. So um that's just it for this section. So in summary, I will just say this, that these constraints collectively they influence the decisions made during the PCB designs, you get. And gives out this point that this, excuse me, sorry. So these constraints they influence how you model your, hello, hello. Okay, should I go on? Okay. So these constraints collectively influence the decisions made during the PCB design process, both with the manufacturers and you communicating with the team, with your team of mechanical design engineers. You get to know how and what's best to design your PCB with. So that's just it. Then we'll be moving over to the next slide, which talks about product functionality. So product functionality refers to the ability of the PCB to perform its intended task, and these include electrical performance of the board, the reliability and the manufacturability. I know that by now these points should be clear to us by now. The electrical performance of the board is actually the board actually functioning as it's supposed to, and then the for the reliability we say that it's the ability of the product, the PCB that you design to actually work for a long time. People can depend on it, people can rely on it. All right, there won't be any issues except maybe one or two external factors happened, or maybe one or two regulations are broken. Then the manufacturability, under the product functionality is actually the ability for it to be manufactured over and over again. So that brings us to the close of this section.